Anytime. So the first page talks about what constitutes an activator versus a deactivator, and then their relative strength as an activator or deactivator. And remember, this is all measured in terms of reaction rate. So compared to benzene, right, what does having this group attached to the ring do to the rate of a common electrophilic aromatic substitution reaction? And generally, if we have a atom like oxygen or nitrogen with a lone pair here, it's going to be a strong activator. This one you can kind of group in with the strong activators as well. I think they're basically just drawing a line in the sand in terms of reaction rate. So if they draw it, between these two, essentially, then this one kind of gets lumped in with the moderate activators. But in terms of structure, it's much more similar to the top ones. So I always kind of think of this as a strong activator, or at least the strongest of the moderate activators. Right? So it's sort of, structurally, it kind of belongs up. But based on where they drew the line in terms of reaction rate, it is getting lumped in with the moderate activators in this chart. Okay, and then we have atoms with a lone pair and also have a carbonyl outside of that. So the reason why these aren't as strong as an activator is because their resonance is partially tied up outside of the ring. So that way they don't donate as effectively into the ring. We have alkyl groups as our weak activators. By the way, all of the activators are orthopara directors. Okay, and then we have halogens, which are technically weak deactivators. Their rate is a little bit slower than benzene, however, they're still orthopara directors. And hopefully he went into an explanation for why this is in the video. But the idea is that they do donate weakly through resonance, making them orthopara directors, because basically it's more stable having a positive charge here. We can have some donation, the lone pair on the halogen, although they're not very strong in terms of their resonance donation. So that means that inductively, the induction effect of drawing electron density towards the halogen is more significant than the resonance effect, which is not true for an oxygen or a nitrogen. These donate much more strongly through resonance. So resonance is more dominant than the withdructive inductive effect. Okay. Anyway, even if he didn't explain it, this chart at least summarizes the overall effect. And then whenever you have a carbonyl, some sort of pi bond where the atom here is electronegative, this will be a moderate deactivator. So you can think of this as sort of similar to that in structure. And this is a pi bond, kind of like a carbonyl. Okay, so those are all moderate deactivators and meta-directors. And then the strongest deactivators are the nitro group, for example, trichloro or trifluorohalogen, needed methyl group here, and then the nitrogen with a positive charge. It's just a strong inductive withdrawer of electron density. Okay, so we want to kind of remember sort of where these fall into the chart. It's going to be important to be able to do predicting the products in multi-step synthesis chapter. Okay, so we are going to be predicting the product where we have a group already attached. Okay, so we want to know what's the most activated position and place the incoming group in that position, right? And then just remember that we cannot do any kind of Friedel-Crafts reaction, either alkylation or acylation, with a either moderately or strongly deactivated system. Because the Friedel-Crafts electrophiles are just not as strong as some of the other electrophiles. Okay, so they can't overcome the extremely poor nucleophile that is created from a deactivated system. Okay, so if we're looking at this, we want to look at this group, right? This is technically a moderate activator. Activators are ortho-para directors. And just note that ortho-para directors direct para first, and only ortho if the para position is blocked. Okay, so you're always going to place para unless that position is blocked. So this is the para position to that group, right? So we will go ahead and draw in the product. And I'm just going to go ahead and rotate that a little bit so it fits. I don't want to draw too big or I won't have enough space. Okay, fluorines are ortho-para directors. Right? So remember that those direct para first. Right? So that's the most activated position. So we can go ahead and put the incoming bromine right in that para position. So firstly, you want to figure out what you're adding, right, and then figure out where it's gonna go. This one is a dimethylamino group is normally a strong activator, an ortho-para director. But remember, under acidic conditions, and both nitric acid and sulfuric acid are strong acids, it will actually protonate the nitrogen, creating a strong deactivator, a meta director. So I'm going to, I think he did not draw the product correctly on this one. Right, so we want to put it in the meta position, the incoming nitro group. We want to recognize that nitric acid and sulfuric acid combination is a nitration, right? And then this one's particularly challenging because you have to remember that amino groups are basic. Okay, so under acidic conditions, it gets protonated. Okay, so these are both strong acids. Okay, so the nitrogen will be protonated. And that will make it a strong deactivator. Meta director. And this is talked about a little bit more in activity 3. And actually, there's another problem related to that. Okay, so this group is because the carbonyl is directly attached to the ring here, this is a moderate deactivator. And it would be a meta director, right? Because it's a deactivator. However, remember that we cannot do any kind of Friedel-Crafts reaction, right, on a reaction that is either moderately or strongly deactivated. Okay, so this will be no reaction. If it did form a product, the group would go in the meta position, right, because this is a deactivator. So there's another problem with this key. I think he ends up putting the group para and then saying no reaction. But it wouldn't go para because this is a moderate deactivator, meta director. Okay, so this position is the activated position. And note that I am not kind of highlighting both of these because they're equivalent, so it doesn't matter, right? So I think he will put a dot on both of them, right? But to me, it doesn't make sense to do that because they're both equivalent and only one would get added. So when you have equivalent positions, I often don't highlight both of them. Just one of them. Okay, so no reaction on this one, right? So no Friedel-Crafts on a moderate deactivated aromatic compound. Okay, and then in this case, the oxygen is now directly attached to the ring, right? So now this is a moderate activator. So well, this one was a moderate deactivator. is a moderate activator. And it's all about that position, right, of the oxygen. Is it directly attached to the ring, or is the carbonyl directly attached? This one is a moderate activator and ortho-para director. That will direct the para first. And the product that's being formed here is we're introducing a sulfonyl group. Those are the conditions of that group.
I'm so sorry, I came in a couple minutes late, but it seems, so you must have said this before, I'm sure, but the trend is that if the oxygen is directly attached to the ring, that's an activator, and then if it's indirectly, like through a carboxyl kind of group or something like that, then it's a deactivator. Is that a good way to?
Yeah, so it's the idea is that what's directly attached to the ring, right? When you have the oxygen directly attached, this will be A. And it's because it also has the carbonyl, right? It's a moderate activator. So if it did not have the carbonyl, and if this was just something else, like an OH or something, then if it was an OH group, it would be a strong activator. But with the carbonyl here, it's a moderate activator. The difference here is now what's directly attached to the ring, right? The carbonyl. So this makes this a moderate deactivator. Then so this is an ortho-para director, whereas this is a meta director. And then we talked about the fact that even though it would direct meta, because you're doing a Friedel-Crafts reaction, you have to write no reaction. So you cannot do a Friedel-Crafts reaction on an aromatic ring that has a moderate, it is moderately or strongly deactivated overall. So this one, we said it was an ortho-para director, so we're going to introduce the sulfonyl group para because that position is not blocked. These conditions look a little bit strange, but this is basically equivalent to a Friedel-Crafts alkylation. Because in a Friedel-Crafts alkylation, the active electrophile is a carbocation, which is formed from an alkyl halide and a Lewis acid. But you can also form a carbocation from an alcohol with a regular acid, because it would protonate it and then that would leave as water to form a tertiary carbocation. So it's essentially the same sort of carbocation. This is the active electrophile, which is the same active electrophile as you would generate in a Friedel-Crafts alkylation with an alkyl halide and a Lewis acid. But regardless of that, right, we know no Friedel-Crafts reactions on a ring that is either moderately or strongly deactivated. This is considered a strong deactivator, right? So we cannot do it. So even though it would direct to that meta position, right, we can't do Friedel-Crafts. So again, any questions on that? I know I had some differences. Okay, so now we're going to be drawing more mechanisms, which I'm surprised by because I felt like we drew every mechanism 3 times in the last activity. But anyway, we're going to do it again. So we have we're going to do a Friedel-Crafts alkylation reaction. So to start that out, right, we can take the alkyl halide, draw in the lone pairs, and then draw in the Lewis acid, and have the Lewis acid base reaction take place. This essentially activates the halogen to be an even better leaving group. When that forms, the iron takes a negative charge and the bromine gets. So now it's an even better leaving group. The only thing is we are going to not draw any primary carbocations. This I do differently than the key. I have no idea why he draws primary carbocations, but that's a terrible idea. So at the same time as we lose the leaving group, we're going to do a hydride shift in order to avoid forming a primary carbocation, which we know is too unstable to form. We're going to go directly to much more stable secondary carbocation. Okay, and we'll draw this in later as we need it to do it. Right, so from here, now we can get the aromatic ring solved. Draw the ring. Remember that the group here is a ortho-para director. We're going to carefully use the pi bond associated with the para position to do the nucleophilic attack. This is where we get our uranium ion, okay, which we can draw out resonance contributors for. I don't know that I have enough room here, but you can practice drawing those out on a separate sheet of paper. So this shows us why the para attack is so favored, because we're the generation of an extra resonance contributor. So to draw resonance, we are just going to start out with the allylic carbocation pattern. Shift the pi bond over. Note that this intermediate is not currently aromatic because this carbon is sp3. So it is a relatively high energy intermediate for this reaction. Okay. Because the oxygen is right next to this positive charge, it can get involved in resonance, and it can help donate electrons to help stabilize this positive charge. Remember that it is inductively, it's withdrawing electrons, but through the pi system, it's donating electrons. And it donates very strongly. So it overcomes the inductive withdrawal of electrons. So now we're at the third contributor, and we even have one more contributor. Move electrons back to the oxygen and shift that pi bond over simultaneously. To get the fourth contributor. So having that oxygen there gives us a fourth contributor, which wouldn't be possible if we had placed this group at a meta position. So this uranium ion is particularly stable because of this resonance contributor. And we can only form it if we do an ortho or para attack. If we do a meta attack, we're not able to evolve the oxygen dissolved resonance. So it's not as stable a intermediate, which means it's going to be a higher energy activation, the rate determining step to get to that intermediate. It will be a slower reaction. Okay, so this is all the resonance contributors for the uranium ion, also known as the sigma complex. But technically, to draw the mechanism, we don't need to draw those unless we're asked to do so. And so we can form the uranium ion. Now we just need to do the final proton transfer. You can either just use bromide or the leaving group we picked out before. do the final proton. Place a little box. Then for the nitration, we have to generate the active electrophile, which is nitronium ion. First, we have to draw out nitric acid. And sulfuric acid. Sulfuric acid is one of the only acids that's really strong enough to protonate nitric acid. Protonate nitric acid. Generates a good leading group, which can now lead. That gets us our active electrophile. The nitrogen here is very electrophilic. We pick out water. Now that we have the active electrophile, the aromatic ring can get involved. And now we're using nitrobenzene. The nitro group, as we know, is a strong deactivator and a meta director. This position is activated. And really, it's not activated, it's just the least deactivated, if that makes sense. So it's sort of the best of the worst in terms of all the positions on the ring. So it will do the attack. We want to use the pi bond associated with that meta position. Right, and then you can draw out the resonance contributors if you want to, but just note that the positive charge will end up being shared here, here, here. And neither of these positions puts the positive charge next to the other strong electron finder. So as a result, it's not as unstable as it would be if the positive charge was right next to this powerful electron finder to stabilize. So this is sort of the best of the worst here of what can form. And the last step is just to protein, generate the aromatic ring. One thing I didn't talk about in activity 1 when I pre-recorded it, but I regret it now, is talking about the reaction. Right? So in terms of like an energy diagram, energy here and something like reaction coordinate. So the reaction here is going to be generating an intermediate. There's one intermediate in the reaction, and it's not aromatic. You can think of from whatever aromatic ring, maybe it has an electron donating group somewhere, maybe it doesn't. It doesn't really matter which one it is, some sort of aromatic compound. And then an aromatic compound is a new group. We use E because that group is an electrophile. We added the electrophile. But it's still aromatic, so it's relatively stable. right? It's hard to say if it's going to be exothermic or endothermic. They're probably pretty similar in energy. So I've drawn it a little exothermic, but that's just a guess. And then the intermediate is the iridium ion. And that one is much higher in energy than the reactant or the product because it's not aromatic. However, it is still resonance stabilized, and the more resonance stabilized it is, the lower energy this intermediate gets, which means that the activation energy, right, which is this one, definitely the larger activation energy. So this is the rate of step, will be lower the more stable this is. So that'll make that pathway faster if we form a more stable. So I just want everybody to kind of understand what the energy diagram looks like for an EAS reaction, an electrophilic aromatic substitution reaction, generically. So 2 steps, 1 intermediate from the aromatic strand. Okay. Moving on to
a question on this. Would you ask us to draw like the full mechanism, or is that just more for us to know how it works?
Yes, you were going to get a one of the electrophilic aromatic substitution reactions to draw. So there's definitely been tons of practice with activity 1, and now this activity introducing a couple even more. So that's you can take a look at the practice exam. I think I just released it yesterday, but it has a fill-in question where you have to draw the full mechanism. And the problem that is on the real exam, real quiz will be very similar, but not exactly the same. Okay, so this talks about now, okay, what if there are multiple groups, right? How do we know where the incoming electrophile will go? That's sort of determining the most activated position, and whatever conditions there are, that group goes to that position. So it's really having a firm handle on sort of groups, right, and where they direct. Sometimes multiple groups will kind of direct to the same position, right, as the other group, and that's kind of very convenient. That happens. And sometimes they direct to different positions, in which case we're going to consider only the strongest activator group there is, and then that one will do the directing. And if they're the same, then it's usually based on steric units. Okay, so looking at this one, we have, this one is a moderate activator. This one is a moderate deactivator. Right? So the moderate activator is directing ortho para first, ortho only if para is blocked. And this one is directing meta, so this one is actually directing to these. But we only look at the strongest activator when they're not directing to the same. In which case, it's going to be this one, so we're going to put the next group in that spot. Okay, so looking at this one, right, if we look at, what do we have here, right? So this is a strong activator. Sometimes I like to put in like a little arrow here, directed there. And then the nitro group is a strong deactivator, which means it will go meta. So it's also directing here, right? And it is directing to this position as well. So, and then this is an ortho para director, so technically it also directs that position. But this one is much less sterically hindered because it's not next to these other groups. So this is going to be the best position to have next to. All right, looking at the next one, we have this group is the carbonyl, right, is directly attached to the ring. This is a moderate deactivator. And then this group is also a moderate deactivator. This is kind of like a carbonyl, triple bond, but it's kind of like the pi bond directly attached to the ring. So another moderate deactivator. So both of these are directing meta, okay, which is here and here. So they're both directing to the same position, which makes it know where the next group should go. And then this one, right? This one looks strange because you can't see that there's an internal plane of symmetry in the way it's drawn. But if you just look at the fact that these are identical groups, right? They are, that's going to create sort of this identical groups. And they are, the oxygen is directly attached to the ring here. So they are moderate activators, which means they're ortho-para directors. Usually that will direct para first. Right, so this one directs here and here, but this is going to be too sterically hindered. And this one directs here and here, and this is too sterically. Right, so the good news is these positions are equivalent. So you just pick one. So these are equivalent. If you were to place it here or here, it would be the same. Equivalent. And then looking at this one, now we have a moderate activator. That's primarily going to do ortho-para, but primarily para. And then the nitro group is a meta-director. This is a strong deactivator, meta-director, but that is going to be to the wrong position. This one is sort of pointed here, here, here. And the nitro group is pointing us meta, which is that one. So we don't, this is not going to be right, because we always go with the stronger activator when they're not directing to the same position. And then typically para, right? Ortho. And these ones get a little bit more complicated, but if you think about it, it's not too bad. Right? It's kind of tied together in a second ring. This position, so you can think of this group as our moderate deactivator. And this is a alkyl group, so it is a weak activator. So we're going to go with wherever the weak activator directs, and it will direct para to it first, unless it's blocked, and then it will go for it. And it turns out that the moderate deactivator is also directing that position because it's meta to that position as well. They both are directing to the same position. It's doubly strong at directing. Same thing here, really. This is a moderate deactivator and a moderate activator. So they're both, again, pointing to that, directing to the same position. Meta to the activator and para to the activator. Here we have a moderate deactivator and a, in terms of this ring, right, this is technically donating is a moderate activator to both rings. Moderate activator to both this ring and the other ring. So in terms of what's the best position, right? This ring has a moderate activator and a moderate deactivator, or this ring only has a moderate activator. This is a much more activated ring, okay? And because it's an activator, we're going to compare that to that. When you have multiple rings, you have to look at which ring is going to be the strongest nucleophile, has more activation from the groups attached. And same thing here. Now we have two rings. Right? This one has a weak activator. This is going to be a moderate deactivator to both rings. And then now we have another moderate deactivator. So this ring has two moderate deactivators, whereas this ring has a moderate deactivator and a weak activator. This is going to be more activated overall. Okay. And then note that a weak activator would go ortho para. Para is now blocked here already. So we have to go ortho. And these two positions, again, are equal. It doesn't matter where you place it, one of those two. Any questions on this part? So it's about analyzing the entire ring and all of the groups to figure out where to place the incoming.
I'm confused for the one that's the second to last one, moderate deactivator and moderate activator. Where would there be anything that would go on the second benzene ring?
So it's just basically if you're adding a group, where is it going to go, right? And so it's going to go to the most activated position. And this ring has two groups. It has a moderate deactivator and a moderate activator. But this ring over here just has the moderate activator. There's no other group attached to this particular ring. This is a more activated ring in general because it doesn't have this electron line group attached to it. So if you're only going to put on one group, right, it's going to go to the best position it possibly can, which is this position. We're not going to add anything. Is that okay, Sheila?
Dr. Gilly, I'm a little confused on why the middle oxygen, the moderate activator, isn't a strong activator.
Okay, let's go back to the chart. So technically, right, if we're looking at this, OR goes into the moderate activator. So this R could be any alkyl group and even a phenyl group. Okay, so, but you're right that structurally it more closely resembles these than it does these other three, right? Like I see what you're going with, and I would kind of group these three together. Structurally, they're very similar, right? They have either a nitrogen or oxygen with a lone pair directly attached to the ring, followed by a carbonyl. And then these structurally look very similar, sort of like including that one, because there's not going to be a carbonyl here, so it's more similar to these than it is to those, right? And I would say this one is probably the strongest of the, quote, moderate activators. Right? It's going to probably have the fastest rate amongst any of these four. Right? It's just when you're talking about the difference between moderate and strong, it's just about reaction rate. Like how fast is the reaction rate for this one compared to benzene, this one, this one, this one, this one's all compared to benzene. And somewhere they drew a line and they said anything this fast is going to be called strong, and anything not as fast as that is going to be called moderate. And they just drew the line in such a place that unfortunately this one kind of got grouped with these instead of grouped up here. So I'm calling it a moderate activator, but I think of it as kind of like a strong activator. It's basically the strongest of the moderate activators. And it just, the reaction rate didn't quite put it over here when they randomly drew a line in terms of reaction rate. I think it doesn't make sense either, but it's kind of the way the data worked, and whoever the person was that decided to, group them together this way. Does that make more sense, Victoria?
Yes, thank you.
Okay, sure. All right, so other questions? I know it's kind of complicated, everything I drew out here. But you just look at the strongest activator, and that one is more important than anything below it. Sometimes they work together and sometimes they don't. Either way, you're just really looking at the strongest. And remember, with ortho-para directors, place the group para unless that position is blocked. In this case, it was blocked. Then you would go. And it's just because it's usually better in terms of steric hindrance. Go para versus. Okay, so now we're going to be practicing basically. So now we have a group, right? And eventually it's going to be examples with more than one group. So we're going to be figuring out, where does this group go? We still have to pay attention to the fact that anytime it's a Friedel-Crafts reaction or the equivalent of a Friedel-Crafts reaction, like on the first page, you can't do that on a moderate or strongly deactivated ring. So that's always that one thing that we always want to keep in mind. Okay, this is a moderate activator and ortho-para director. So it's going to direct para first, and we are doing a Friedel-Crafts alkylation reaction and introducing a methyl group. Okay, so we're just going to place a methyl group in that para position. Okay, this one, we have two rings. We have to look at both of them. Okay. This ring is moderately deactivated, whereas this ring is moderately activated. So this ring is going to be better because moderately activated is much better than moderate. And moderately activated, so it's an activator, so it's going to be an ortho-para director. So we're going to put the para to that oxygen. This is also a Friedel-Crafts alkylation reaction, but remember, if you get longer than 2 carbons, then there's always a rearrangement. Okay, so you can add methyl or ethyl, no rearrangement. But if it's primary group and it's longer than 2 carbons, so propyl or longer, then it will rearrange. And the active electrophile in solution will be the secondary carbocation. We're going to be introducing that group in reality. And we really need to care about that mostly when we have a primary carbon that's longer than propyl or butyl. The next one, we have, all of these are ortho-para directors, right? But the OH group is a strong activator, and the bromines are actually weak deactivators, even though they're still ortho-para directors. So definitely we're going to be caring where the oxygen of the alcohol is, and para position is not blocked. And conditions tell us to add a nitro group, with nitric acid and sulfuric acid. Remember, anytime it's a Friedel-Crafts reaction, you should always pause. Go, can I do that? Right? Is this a good enough ring? Does it have anything that would prevent you from doing that Friedel-Crafts reaction, but you can always add a nitro group, so that's not a problem. You just have to figure out where to put it. All right, so this is again another Friedel-Crafts reaction. It's an acylation reaction. We have to be careful here. Right? We can't do this if the ring is either moderately or strongly deactivated overall. This is a strong deactivator. Okay, so this is no reaction. Even though it is incoming groups go meta, they can't be acyl or alkyl groups. Okay, so these conditions are telling us to introduce a sulfonyl group, okay? And we want to figure out, which is no problem. Not a Friedel-Crafts reaction, so we don't have to worry about it too much. We know we're going to be making a product. And then there's two rings, right? This ring has a moderate deactivator attached to it. This ring has that same moderate deactivator, but it also has a moderate activator. This is much better. This ring is much better because it has that activator. And para, so that is not blocked. So that's what we're going to put our in. I'm going to have to get a little bit. All right, this one, right, there's some symmetry here. So there's symmetry here. But technically, one of these rings is like an alkyl group, and it's going to be a weak activator for the other ring. So if you think about this one is weakly activating the para position on the other ring. Same thing, this one is weakly activating the para position on the other ring. Well, it turns out those two positions are equivalent because of the symmetry. So it doesn't matter where you put the phone. So that is that okay? You can practice this a lot with problems. Okay, so we're going to be doing some multi-step synthesis. We want to add a nitro group and a acyl group. So we have to be careful because remember we cannot do a Friedel-Crafts reaction on a deactivated system, moderately or strongly deactivated. So that means I have to carefully consider the order here. Okay? In terms of directing groups, the nitro group's a meta director and the acyl group is a meta director. So potentially they can both direct to the right position, right? But we can't add the acyl group once the nitro group is already there, which means we should add the acyl group first. Right? We cannot add this second, because once the nitro group is there, you can't do a Friedel-Crafts reaction. You need to carefully add the acyl group first, then add the nitro groups. So starting from benzene, we are going to add the acyl group first through a Friedel-Crafts acylation reaction. And then now we can add a nitro group. You can always add a nitro group. We just have to be careful when to add the acyl. So we just have to remember that to add a nitro group, we need nitric acid and sulfuric acid. That will go meta to the acyl group because this is a moderate deactivator and meta director. And in terms of these positions, whenever you see two groups ortho, it almost always involves a protecting group. Because if you, in order to get something ortho to something else, right, that ortho para director would have directed the next group para. So we need to block it. So we'll definitely be using the blocking group and protection strategy in order to get this ortho. So starting from benzene, right? Would it matter which one you add first, right? Do you add the bromine first or the isopropyl group? Both of these are ortho-para directors, so it doesn't really matter from that point of view. But just in order to have the best yields all the way around, it's best to add the strongest activator that you can. Then the next reaction is even faster, as opposed to adding a deactivator, which makes the next reaction a little bit slower. So when given the choice, it makes more sense to add the isopropyl first. So to do that, you can do a Friedel-Crafts alkylation reaction. We've now introduced an ortho-para director, right? So the next position will go, the group will go para. So we need to block that position. We don't want our bromine to go there, so we need to block it. To block it, we're going to use concentrated H2SO4, add in a sulfonyl group, now our ortho-para director will have to direct ortho because para is blocked. In addition, we've introduced a meta director. This is a meta director. So it's kind of pointing to the same position as the isopropyl group. They're reinforcing. These two positions are equivalent, so it really doesn't matter where you put the next group, which is a bromine. So to add a bromine, we need Br2, some sort of catalyst. You could use iron tribromide or just iron. Or aluminum tribromide is also good. Put our bromine in there. Now we can just remove that sulfonyl group, dilute acid. That's the beauty of the sulfonyl group, is you can use it as a blocking group and get rid of it later. Okay, for the next one, right now we have an amino group. The only way to get an amino group is to introduce a nitro and then reduce it. Okay? And we have this alkyl group. To get the alkyl group, we either could have done a Friedel-Crafts alkylation or possibly a Friedel-Crafts acylation followed by reduction. So note though that either way, if you do an alkylation or an acylation, it's still a Friedel-Crafts reaction. And we can't do it if there's a nitro group on the ring. So it makes sense to do this reaction first, then introduce the nitro group, kind of like we did up here. We don't want to do a Friedel-Crafts alkylation, so we don't want to introduce the ethyl because that will be a para director. And that means the nitro group won't go to the position we want. So we have to introduce the acyl group and then rely on reducing later. So it's going to really start out very similar to the first problem. We're going to do an acylation followed by introducing the nitro group. Now this is a meta director, which is great because we need that next group meta. We're going to do a nitration now. Well, our meta director is there. Remember that it's important to add the nitro group second instead of the acyl group second, because the acyl group cannot go on second. Now that we have this, we just need to reduce the nitro to an amino group and then reduce the carbonyl. So note the conditions here, right? For this is a little bit tricky for students. So if you look at what the book talks about as a condition to reduce the nitro group, to an amino group. Usually it just says zinc and HCl. By the way, there is a basic workup that is not mentioned, but it definitely needs to happen. Because under acidic conditions, this would be protonated. Amines are basic. Under acidic conditions, they would pick up a proton and become an ammonium ion. So in order to get the free amine back, we need to do a basic workup, which is not mentioned. That needs to happen. And then, so the point here was that how do we compare this to the conditions to reduce a carbonyl through a Clemmensen reduction? So these conditions typically are listed as zinc mercury, which is an amalgam, and HCl. So the zinc mercury amalgam is needed to reduce the carbonyl, right? And zinc is needed to reduce a nitro group. But there is zinc in a zinc mercury amalgam. So if we want to, let's say we have a case where we have both of those groups. Do we have to do these separately? No, we don't. So in our case, we had both of these, and they both want to reduce them both, right? So we're going to just use the zinc mercury amalgam. That will reduce the carbonyl, and the zinc in it will reduce the nitro. So you'll end up reducing both of those in one step. You can do both reductions in one step with the Clemmensen reduction. When I say Clemmensen reduction, conditions. The main reaction. Does that make sense? Because you're not trying to isolate an amino group here, you don't need a basic workup. Right? Because we are here, and it's HCl conditions, there would be the need for a basic workup. And again, we don't mention it, but we just assume that is happening. Okay, so all of this to point out that you don't need to do the next step separately. You can just use the Clemmensen reaction conditions, zinc mercury amalgam and HCl, to produce the product here in one step. And again, there definitely needs to be a basic workup, but it's not mentioned. So this does essentially add 2 reductions here. Okay. I am going to go over this one last. And I don't have room for it anyway, but I'll just do it on a separate. We are going to do this one next, right? So if we think about what we have here, we have a bit of a problem. We have 2 groups, and they're both ortho-para directors, but they're meta to each other. So how can I get an ortho-para director to direct a group meta, right? Either one will direct the next group meta. But one of the things I can recognize is that if I had a carbonyl here, I could reduce it. So a strategy that I could use is to do, instead of an alkylation, introduce the methyl group, I could do an acylation. That uses this special kind of acyl halide kind of / aldehyde. And I'm going to then just introduce the aldehyde that way. The aldehyde is a meta director. So that's really great because I need the bromine to be directed meta. So that's kind of why I wanted that group there. So now I can introduce the bromine meta to that group. And then the last step, it's a bit strange. He used hydrazine and And then in the second step, potassium hydroxide, I believe, or basically he used what's called the Wolff-Kishner reduction conditions. But those conditions are not introduced until chapter 20. Currently, this activity is chapter 19. So it doesn't make sense to me that he used those conditions because you won't learn those until chapter 20. And for those of you who worked a little ahead, you might have heard of them. But otherwise, we actually can just use conditions from chapter 19. So we can just use the Clemmensen reduction to reduce that carbonyl. So we actually didn't need to do the Wolff-Kishner reduction. That's kind of doubly weird that we used it. The last one here, now we have a nitro and a bromine. If we introduce the nitro first, the bromine will go meta. That's a problem. But the bromine is an ortho-para director. Right? So it makes sense to introduce the bromine first, and it will direct the next group para to it, and you can introduce the nitro second. Just in order to do the reactions, you need to introduce the bromine first. This is a para director, so we can just do a nitration, and it will go to the correct position. This one is a particular challenge. This is very difficult to do. That's going to be a very, what we call a lengthy synthesis, or steppy, meaning it has a lot of steps necessary to get this done. Because the problem is, while these are both meta directors, and it might look like, oh, I'll just introduce one and then I'll just introduce the next one, right? But the problem is that this is a moderate deactivator, and the next reaction is a Friedel-Crafts reaction. So we can't do a Friedel-Crafts reaction and then another Friedel-Crafts reaction, because the Friedel-Crafts acylation reaction introduced a moderate deactivator, which prevents us from introducing another Friedel-Crafts reaction. So we're not able to do that. So that's kind of where the problem comes. So we can introduce one of them, right? But that prevents us from being able to do another one. And it's just too deactivated. So we can introduce, if I introduce one of them, right? Then it is a meta director, and it's directing meta, which is good because I want my group to go meta. But I can't introduce this group because it's a Friedel-Crafts reaction. This is not the right system to do a Friedel-Crafts reaction. But one thing I can do is potentially add a bromine. So I can add a bromine, I just can't do an alkylation on acylation. But from the bromine, I can think about making the new carbon-carbon bond through a Grignard reaction. The problem with doing a Grignard reaction is we can't have a ketone in presence of a Grignard reagent, otherwise the Grignard reagent will attack a ketone from the molecule. So we have to protect this, right? So it's no longer a ketone. We have protection conditions, but they're not introduced until chapter 20. So those of you who looked ahead might realize I could protect this through an acetal. But we don't know about acetals yet. We haven't reached chapter 20. So really the only way we know how to protect is to protect an alcohol. We'd have to reduce this to an alcohol to protect it. So we'd have to essentially reduce with either sodium borohydride or lithium hydride to an alcohol. And then we'd have to protect that alcohol with a TMS group. All because we need to do a Grignard reaction, and it wouldn't have been compatible otherwise. Now we can through the Grignard reaction, which will involve treatment with magnesium and an aldehyde. And an acidic workup, which is often not mentioned. Assuming the acidic workup does not deprotect the TM ester and it's still there, so we'll have to go ahead and deprotect it. Once we're at this diol, we can do excess PCC to oxidize both of them back to carbonyl. So it's a pretty lengthy synthesis, as you can see. It's 1, 2, 3, 4, 5, 6, 7 steps. Sometimes, using electrophilic aromatic substitution reaction, it's not so easy to make the product we want to make. Sometimes that it can be very convenient. Sometimes we can't really make it through electrophilic aromatic substitution. Okay. Moving on, we're going to start talking about the nucleophilic aromatic substitution reaction. It uses abbreviation NAS, but you also might see it as SNAR, which basically stands for substitution with a nucleophile on an aromatic ring. Okay, so kind of like SN2 or SN1, but specifically on an aromatic ring. So the difference here is with electrophilic aromatic substitutions, the reagent was always an electrophile, a strong electrophile, and the aromatic ring was the nucleophile, right? This is going to be the opposite. The reagent that we add is going to be a nucleophile instead of an electrophile. And that means the aromatic ring is going to have to act as an electrophile instead of nucleophile. So a totally different reaction than an electrophilic aromatic substitution. But it is an aromatic substitution, so that's why it's in this chapter. Okay, for this to work, right, we're going to need to basically substitute the bromine with the nucleophile, right? Hence why it's a substitution. But we cannot draw an SN2 mechanism. We cannot draw an SN1 mechanism. So I think you guys probably learned last semester, we cannot do an SN2 on an sp2 hybridized carbon. The carbon attached to the bromine here is sp2. Cannot do an SN2 reaction. We also cannot do an SN1 reaction on sp2 hybridized carbon because the carbocation that would form through loss of a leaving group is vinylic and too unstable. So the mechanism is not SN2 and it is not SN1. It's very different. So it's going to be multi-steps. The first step is a nucleophilic attack at what you might call the alpha carbon for the leaving group. Right? So this would be the alpha carbon, here's the leaving group. We're going to attack there, but we are not going to just show the bromine leaving, like in SN2. That's not the way this works. Okay? But what we can do is temporarily move pi electrons away from that carbon. So that generates an intermediate like this. Notice that this is not an intermediate you would see in an SN2 or an SN1. Very different. By the way, this does have a name. This intermediate is called a Meisenheimer complex. They always pick the hardest to spell words, right? Like the Markovnikov. Knows how to spell that one, right? So the Meisenheimer complex. Notice that it is different than a sigma complex, or also known as the rhenium ion. The rhenium ion has a positive charge on the ring, and the Meisenheimer complex has a resonance stabilized negative charge. So that's very different. And that's because of the difference of how this is acting, right? This is now going to be an electrophile, not a nucleophile. When it gets attacked, it's electron rich. Okay, so this is just one of the resonance contributors. Okay, you could keep going, and there's one more. So basically, the negative charge is shared between this carbon, which we can see in the resonance contributor, and this. So there's 3 resonance contributors. And this is a favored reaction that works because the negative charge ends up next to the electron withdrawing group. Remember that this is a strong electron withdrawing group. That's good because it can help take away some of the electron density from the negative charge. Right? So having an intermediate where the negative charge lands right next to a strong electron withdrawing group makes this the most stable resonance. And it's very important that you're able to draw a resonance contributor where the negative charge is next to strong electron withdrawing group. That helps stabilize it and makes this intermediate lower energy and easier to form. Okay, so from there, the mechanism, we're just going to kick out the leaving group. We'll regenerate the pi bond and do loss of a leaving group. And we end up with the leaving group that is gone and the substituted product. So note how we got an OH group attached to the ring, right? Think back to your electrophilic aromatic substitution reactions. Is there any way to get an OH group directly attached to the aromatic ring, basically to generate a phenol through an electrophilic aromatic substitution reaction? No. We can introduce a bromine or a chlorine. We can introduce an alkyl group or an acyl group. We can introduce a nitro group or a sulfonyl group. We cannot introduce an OH group for an electrophilic aromatic substitution reaction. So this is the only way to get this sort of group. So synthetically, when you're doing problems and you see a group like this, you need to have light bulbs going off in your head going, okay, at some point I need to do a nucleophilic aromatic substitution in order to get that group there. Okay, so if you have an oxygen directly attached to the ring, you must do a nucleophilic aromatic substitution. Cannot introduce that through an electrophilic aromatic substitution. And what are the requirements for a nucleophilic aromatic substitution reaction? You have to have a leaving group, because note, you are actually kicking out a leaving group. That's very different from an electrophilic aromatic substitution reaction. In an electrophilic aromatic substitution reaction, we replace a hydrogen, right? So that's very different than an actual good leaving group. We also need at least one strong electron withdrawing group, right? So there could be more is better, but at least one. And it needs to be either ortho or para to the leaving group. It cannot be meta, because if the electron withdrawing group is meta to the leaving group, you don't generate the stable Eisenheimer complex. And that means activation energy for that is too high and the reaction does not proceed with a reasonable rate. And it doesn't work. So that's this example here where the leaving group is meta to the strong electron withdrawing group. This reaction does not work. Aromatic substitution. And the reason for that is when this attacks, the Eisenheimer complex that we form draw out all the resonance contributors. That's the initial anion formed from the nucleophilic attack. We can show resonance, right, to move that negative charge to every other atom in the ring. So it is resonance stabilized. But it's not resonance stabilized enough to make it stable enough intermediate form. So I can draw one more resonance for my Mesenheimer complex. But the problem is that, notice where the negative charge is. It ends up here, here, here. Those three carbons share the negative charge. But it never ends up at the carbon next to the electron withdrawing group. So this electron withdrawing group is too far away to really help stabilize that negative charge. Okay, so we never generate a super stable resonance contributor like the one up here, where the negative charge is next to the electron. And so this one, this Mesenheimer complex just is not stable enough. So what does that mean? The energy diagram for this reaction would be similar to an electrophilic aromatic substitution reaction. You'd still get the two pumps, right, for the reaction. But if this isn't stable enough, it's like the intermediate energy is up here, and it just has to climb too high of an energy gap, okay, to get up to this less stable intermediate. This slows the rate down reaction. So that's why the electron withdrawing group must be ortho or para to the leaving group. Because when it is, we're able to form this stable Mesenheimer complex, which means the activation energy is more reasonable reaction. Let's look at a synthesis where we have to draw in the reagents. Figure out what are the correct reagents for each reaction. This one is introducing a bromine. Right? So bromine in some sort of catalyst, could be iron, could be aluminum, could be aluminum tribromide or iron tribromide. Right? Doesn't really matter. Let's vary it from what I've been using, just those four things. From here, this is a orthopara director, so the incoming nitro group is in the right position. You just have to remember what are the conditions to introduce a nitro. And then notice how now we are introducing this methoxy group. We cannot do this through an electrophilic aromatic substitution reaction. It must be a nucleophilic aromatic substitution reaction. Luckily, all of the conditions are satisfied. We have a leaving group and a strong electron withdrawing group that is para to that leaving group. So the reaction will work. Notice that I did not introduce an OH group, O methyl group. That's fine. So instead of sodium hydroxide, we're just going to use sodium methoxide. If we wanted to introduce hydroxide, it would be sodium hydroxide. And if we want to introduce ether, we use an alkoxide. And then the last step is reduction of the nitro group. We can do that with and a basic ortho. This page is a review. So we can, or at least part of it is review. You can do a chlorination. So introducing chlorine ring. That will set us up to be able to do a Grignard reaction. And so we'll be forming the Grignard reagent with magnesium, and it attacks then the epoxide at the less substituted carbon. So then the product after that step is this. Turn acidic workup. Proton here. On this, oh, I don't know what happened here. We'll oxidize the alcohol to a carbonyl, to ketone in this case. And then this might be a little bit weird to you, this, when have we ever seen lithium, right? But basically this is the equivalent of a Grignard. So if you have a phenyl attached to a lithium, it's going to be very similar as if it was attached to magnesium. Right? It's going to be highly polar bond with the electrons residing around the carbon. So just basically think of alkyl lithiums as equivalent to a Grignard reagent, and it will just do what a Grignard reagent would do, which is attack that ketone. Will produce tertiary alcohol. Now we have an epoxide, right? Bromide. Bromide's a strong nucleophile, so it's going to attack less substituted carbon, and it will do inversion of that carbon. So we just want to make sure to go ahead and draw that from behind, so that we have inversion of that carbon, and then we assume there's an acidic workup by that proton. So this one, KSH, is really just SH minus, which is a strong nucleophile, and it looks like it attacked an epoxide here. So let's draw the epoxide and keep the groups as drawn. This is an oxy, well, really an alkoxy mercuration reaction. Okay, so we are going to end up adding the alcohol at the most substituted carbon, Markovnikov. We'll end up with an ether here. And then this is a Grignard reagent with, instead of methyl, CD3. So it's like a labeled methyl group. And remember that it attacks esters twice. So it will end up attached to that carbon twice. So instead of two methyls, we have to write. Then we have three methylenes, 1, 2, 3. So I go 1, 2, 3. And then we will have broken this bond through the loss of a leaving group. We'll go ahead and add alcohol. We did not use deuterated water, just regular water. So the hydrogens in that. That's the end of the activity. Let me know if you guys have questions.
I don't really get how that last one works.
Okay. So the last one, so we have the ester. And then basically we have this weird Grignard reagent where carbon, which is attached to 3 deuteriums instead of 3 hydrogens, right? And it's a Grignard reagent. So it's going to do, just like any carbon-magnesium bond, it's nucleophilic. So Grignard attack on the carbonyl. And that will generate carbon, which has 3 deuteriums attached. Negatively charged oxygen. Basically, instead of adding methyl, we've added CD3. And then this, we can kick out this as a leaving group, just like we would. This wasn't deuterium. And then at this point, this bond is broken, so we're not really at a cyclic structure anymore. You can kind of make it look like a cyclic structure for the time being. Or you can kind of make it go drawn out like this. Now we have a ketone, which will get attacked again by a second Grignard reagent. So the same exact substrate we drew in before. You can draw out the deuterium or not, it's up to you. That's where that second one gets introduced. So you can think of it as 2 CD3 groups now, attached with oh my. As soon as it gets kicked out, it's just. And then at this point, the water comes in and provides the protons to protonate both of those. Can you see that better, Shira?
Yeah.
Okay.